Hello everyone. Yesterday we briefly went over the first chapter, which is kind of introduction about this class, giving a basic concept and associate fundamental principles for this class, statics. So today we'd like to introduce the first technical part, which is chapter 2, talking about the statics of particles. In this class, statics, we always deal with what we call rigid bodies. But as a special case, rigid bodies are particles. In other words, particles are treated as just one mathematical point, or called a material point. Rigid body particles are the collection of infinite number of particles together or bound together to form kind of a rigid body with certain sizes. But before we try to understand the statics of rigid bodies, we need to know this special case, which is the chapter 2 is talking about. It's called the statics of particles. Our plan is to split this chapter into two parts. The first one is mathematically two-dimensional problems, which is called forces in a plane, or two-dimensional forces. And then the second part, which we're going to talk about in later days, is the forces in spaces. That means the forces in three-dimensional setting. How are we going to add forces in three-dimensional setting? So let's first go through the basic concept about this chapter. So right now I'm showing you a picture. You see a person trying to travel from one side to another side, for example, between the two mountains. And you will see the cable on the top is providing a tool for the lady to travel from one side to another. So obviously, as an engineer or like a structural engineer, we're concerned about the safety of this scenario. So in other words, whether this cable is providing enough strength so that the person can safely travel from one side to another. You may say, well, how are we going to do that? Actually, this is a very simple question, in fact, and I would suggest you to come back to this picture after you are done with this chapter. So, in other words, based on the fundamental principles from this chapter you're going to learn, you can easily solve the problem. In other words, we can calculate the tensile force in the cable supporting this person once we learn the basic concept from this chapter. And I encourage you to come back to look at this picture at the end of the chapter and then see how you're going to solve it. Now, let's talk about the objective of this chapter 2, statics of particles. So basically, we're talking about the forces acting on a single particle, for example. If there's only one force acting on the particle, I think that's pretty straightforward. You just need to know how to use mathematics to represent the force. Unfortunately, in real engineering practice, we basically see a lot of real forces acting on a single particle. We call them multiple forces acting on the single particle. If that's the case, how are we going to effectively treat this kind of engineering scenario using mathematics? We are going to introduce a very important concept, which is called resultant force. So resultant force, in fact, is equivalent one single force, which is a virtual force, but it is equivalent to the effect of multiple real forces acting on the same particle. So the question we're going to encounter, in other words, we try to solve or we try to calculate the resultant force, which is a virtual one, but based on the multiple forces acting on the particle. And then we'll see how we can solve the problem. Once we can calculate the resultant force based on the real scenario, then if this particle is in the state of equilibrium, then based on Newton's first law, this resultant force should be equal to zero, because Newton's first law always tells us the total force together must equal zero in order to maintain that particle at rest or travel with a constant linear speed. Okay, so this is a basic objective in this chapter. Again, we are going to split this chapter in terms of two-dimensional setting and the three-dimensional setting into two parts. Now, how are we going to use mathematics to represent a physical quantity? In other words, in this chapter we call a force. So you may say, well, why do we need to use mathematics? As an engineer, we always use mathematics to model any physical real problems. So now, if you see this picture on the top, you have a force with this red color acting on the particle A. So if there's only one force acting on this particle A, how are we going to use mathematics to represent? So typically we use a concept we call a vector. So that's why this entire class is basically called vector-based engineering mechanics or statics. So that's why if you look at the textbook, it is called a vector mechanics for engineers. And the first part is just statics. So we need to know vector. Of course, we're going to talk about vector, but I just want to tell you in essence, every time when we see a force, we use a vector to represent such force. Talking about the vectors. First of all, we need to know the magnitude of this force or this vector. So typically, you can have a force with a 10 pounds, for example, like this. So now we say, okay, the magnitude is 10 pounds. But that's not enough. Vectors are always with some kind of directions. So then we need to continue to identify so-called direction. In terms of these two terms, one is called the line of action. So that means that's a certain line. For example, this going this one, this is called the line of action. But also you need to tell the sense, which means the direction. So you use an arrow to indicate that's a direction. So we can sometimes combine line of action and the sense together. I just simply call the direction of the force or the direction of the vector. So under this very simple scenario, you have only one single particle acting on point A. Everything's simple. But as I told you before, many times, as always, typically, we need to deal with multiple forces acting on a single particle. Let me just give you another example like this, okay? So multiple forces should start from two forces, three forces, and so on, right? Let's take a simple example, having two forces, P and Q, acting at particle A. So if this is the case, how are we going to consider this engineering problem using mathematical models? So in other words, originally we have two forces, force P and force Q, maybe in different directions. Now we use vectors, right? We need to use vectors to represent the two forces. Now, what is the equivalent, a single force or a virtual force? Of course, here I use R, which is equivalent to these two real existing forces. That's called force P and force Q. So typically you learn something from calculus and some kind of college physics talking about this case. But since forces are vectors, so you have to use a vector way to calculate the summation of two forces or multiple forces. Okay, so how to do that? Our textbook or the whole static theory introduce at least two methods to calculate the resultant force if there are two forces or 100 forces. So this is the first way we use a trigonometry. But I'm not going to talk about the details because number one, the trigonometry is kind of geometry-based method, which is not very standard. Okay, I'm not saying such method cannot solve a lot of problems, but many problems, if you have 100 forces, you use this trigonometry, it takes days to calculate. But the second method, which I'm going to emphasize, that's very easy, very straightforward, very mathematical. Okay, but I do want to briefly introduce this one because this method is good if there are only two forces acting on that particle. Okay, so in order to calculate the summation or the sum of these two forces, P and Q, using the red color representing the real forces acting on this particle, then we're saying the resultant force, the equivalent one, which is the virtual one, that's not real, okay? This is not real, acting on this one. The virtual one, but the summation of these two, which is equivalent, which is equal to P plus Q. Okay, so the first method, we call the trigonometry, is basically use a parallelogram law, right? So you can build a parallel line, which is a line parallel to this, and then you build another one from the end of this force
parallel to this one, and then you can find this point, and then from point A to point this, that is called the resultant force. That's the definition in the more geometrical way. How to mathematically calculate the magnitude of this one and also the direction of that resultant force. Basically, we need to introduce law of cosines and law of sines. Okay? So, from high school, you know, if there is a triangle, you can pick this triangle, you can pick the bottom triangle, it doesn't matter, just pick one of the triangles. So, for example, you are basically using this triangle, the top one. Okay? So, from this triangle, if you know this side, that's from A to B, the magnitude is P, and from B to C, the magnitude is Q. The reason this is Q, which is this, is because this is the parallelogram, right? So this Q equal to this Q in terms of the magnitude. So, in this triangle ABC, how to calculate the distance of AC? Well, obviously, that's called the law of cosines, right? So, P plus Q, if it's defined as R, then R squared, this one, that should be equal to P squared plus Q squared minus 2P times Q and times cosine B. This is the angle we call B, and that is what we call the law of cosines. Okay, so from this first equation, you can calculate the magnitude of this resultant force. So another thing I want to remind you, we always use this. Just keep in mind, if we are saying something is a vector, we always use an arrow on top of this symbol. Okay, so we have R and then we have an arrowhead on top. That means a vector. But sometimes if we do not have this one on top of this R, that means that's a magnitude of this force. Okay, because it's always in print. That's easy. If you need to write down your answers, so you need to make sure if you are using a vector, then you need to make sure you have R, and on top of R, you definitely need to have the arrow on top. If you're talking about only the magnitude, then you don't have to use that. Okay? This is the vector equation indicating the summation of two forces, P and Q. However, if you want to translate this one in terms of the traditional mathematics, that's trigonometry, you need to use this one. That means, which is the law of cosines. Law of cosines gave you the magnitude of this force. However, that equation doesn't provide you with any additional information. So in order for us to further calculate the direction in this direction, we need to use another trigonometry equation, and that is called the law of sines. So in a certain triangle, there's another equation which is called the law of sines. Instead of using something with a cosine of the angle, this time we use a sine of those angles. Okay? So again, in this triangle ABC, sine A, that's the angle A, divided by the corresponding side, that's called Q, the distance, that should be equal to sine B, not cosine, sine B, divided by the corresponding side, that's called R, and also that's equal to sine of this angle C, and divided by the distance of this one, that is called AB. Oh, I'm sorry, this is an obvious mistake, that's P. Okay, this is not A, this is P. Okay, so you need to combine these two equations in order to calculate this angle. That means angle A. Once you get an angle, the total angle that should be given, and then you can determine the direction of this resultant force. Okay? I don't like this method. It's simply because there are some limitations about this method. If there are only two forces, that's fine. Okay, you can just use law of cosines, law of sines to deal with those problems. If I have more forces, something like this, okay, at a certain particle, we're called material point A, instead of having two forces, this time we have four forces. And how are you going to use the trigonometry to calculate the resultant force? Or in other words, these four real forces should be equivalent to an unknown resultant force. And how are you going to calculate that resultant force in terms of the magnitude, in terms of the direction? If you go back to use law of cosine, law of sines, it is doable. Okay? If I do it, I think I have to really think about it. Probably takes 1 or 2 hours to get this done. But I don't want to spend those 1 or 2 hours just use this kind of law of cosine, law of sines to solve this problem if I have another simple way. to solve the problem. So that's why I want to emphasize the other method, which is called the component method. No matter how many forces, you can have 1,000 forces acting on this particle. I can tell you a unified way to systematically calculate the resultant force. Okay, and that's the method I call component method. Or in other words, in the book, they call it rectangular components of a force. So all you need to do for two-dimensional problems, same three-dimensional problems are the same. I'm going to introduce later, right? For the first part, when I talk about two-dimensional problems, number one, you need to find that particle. In other words, find this particle. And then you establish the two-dimensional Cartesian coordinate system. Okay, for example, normally we always call this is the horizontal direction and this is the vertical this is the y direction with the vertical direction. And then for each force, we need to calculate those components with respect to x and y directions. Now we can transfer a vector summation among F1, F2, F3, F4 into the component summation. Because all the forces, the x component together in one direction, you just add them together. That's called the scalar summation. So you don't need to worry about the vector sum. Okay, so first of all, let me introduce this method, and then we come back to solve this problem. First of all, when you have one force, again, we start from one force. We have one force acting on this particle O. The first thing you need to do is to establish the two-dimensional Cartesian coordinate system. And normally we call x is horizontal direction, y is in vertical direction. Once we got these, okay, then we identify the angle between this force and the x direction is called theta. Then we can calculate the x components of this force F, which is called Fx. You can also calculate the y component of this force, normally called Fy. Okay, so these Fx and Fy are called x and y components of that force acting on point O. So all we need to do is to know the magnitude of the force and know the angle. In terms of vector, you can still write just something like this. So this force acting on point O can be split or can be separated into two forces. This is the x component of force, and this is the y component of force. Keep in mind, on the left-hand side, that's force vector. So the right-hand side, these two f's are also vectors. So that's why we put the arrow on top of each symbol. Fx, you call Fx is x component. Y is a vector. It is still vector because this is in this x direction, and that's the vector. Fy, that's also a vector because it's going to the other direction. However, we want to further write this vector Fx into Fx times a direction. So now we are splitting this vector Fx with an arrow, which is equal to Fx, but without arrow on top, multiply with I. This is called a unit vector. So I is a unit vector in x direction. Always, if you look at basically any book, mathematics books, they always use this I representing the unit vector in x direction. They always use J, this J with the arrow on top, representing the unit vector in y direction. In three-dimensional setting, there's a K there in the third direction, which we're going to talk about after we touch on the second part. Okay, so originally this Fx itself is a vector, but it's equal to this Fx times I, indicating this one is a vector, but this Fx, you know, I write the same symbol, Fx, that's the same. But they are different because there's arrow on top, this doesn't. So this Fx is called x component, which is a scalar. Okay, but the scalar multiplied with a vector together is still a vector. So either you can write f equal to fx plus fy with the indication of the summation or the separation of this vector force into x and y components, or you can write the other way. This is the more mathematical way. And that's, in this case, fx and fy without arrow are referred to as the scalar component of this vector force. Okay? In other words, you can also write something like this. But this time, you see, well, sometime in the book, because I basically, this the PowerPoint I got from the publisher, you may see, well, how come this one doesn't have the arrow on top? Because when you have the print setting, right, this F is bolded. So that's why that's equivalent to this. Sometimes they have an arrow on top, sometimes they don't have, then this one is still different from here because this is a bolted. Okay, so next job we need to do is to calculate what is fx, what is fy. We know the direction already because this is fx direction, this is the fy direction, but we need to identify the component, x component, y component, and that's very easy to do because basically, well, they didn't give us, well, that's fine. Let's say we have this, let's use this one, right? Okay, we forgot one equation. So what is fx now? Well, that's very easy, right? In this two-dimensional setting, fx, that's a component that should be equal to f. This is the magnitude of the force multiply cosine theta, right? So f times cosine theta, that's equal to fx. That's x component. And what is fy? Fy is y component. That's going to be f multiply sine theta. Okay, I thought the next slide had those two equations. It doesn't. You can write it down. So again, fx equal to f times cosine theta. Fy equal to f times sine theta. And these are the universal equations to calculate the two components, x and y components. Okay? Now, let's go back to look at multiple forces acting on this particle, like 4 forces or like 3 forces. How are we going to calculate the resultant force? Okay, if we have 3 forces, that's very easy. What you need to do is to look at this point, which is called the particle, and establish two-dimensional Cartesian coordinate system, having this as x direction, having this in y direction, and then you just do forces to get their components one by one. Okay, for example, you have this force P, then you get these two components because you know the angle of this one, and then for this force S, you get these two components, F and X and Y components. For this Q, you get the two components, and then in each in X component, you add them together. You add all these together. That is called the X components of the resultant force, Px plus Qx plus Sx, and you can easily just add them together. Similarly, you look at all the Y component, you add them together, and that is called the Y component of the resultant force. Once you get X component and Y component of that unknown or equivalent resultant force, then this is the Rx, this is the Ry. Then what is the total? The equivalent resultant force. The magnitude equal to Rx squared plus Ry squared and then square root. The reason you can use this is a special case of the trigonometry because this angle is 90 degrees. Similarly, how are you going to calculate this angle? The angle between the resultant force and the x direction, then obviously it's Ry over Rx, and then you take inverse of tangent. Okay, so these are the equations we can use to calculate the resultant force at a certain point if there are real multiple forces acting on this particle. And that's exactly the procedures. Okay, so what I'm going to do is to go back to look at this original example, having 4 forces acting on that particle, and how are we going to calculate the resultant force. Okay, so this time I'm going to talk about this example, and I believe I have the chart. Okay, but let me first introduce this example. There are 4 forces. There are 4 forces, 1, 2, 3, 4, right? Acting on bolt A, that's particle A, as shown above, and determine the resultant or the resultant force on this bolt. Okay, so basically there are real 4 forces acting on that particle. But instead of dealing with the 4 forces, we are going to use an equivalent force, which is called the resultant force. Once we can determine the equivalent force in certain direction, we can erase those 4 existing forces. Then we just say there is one equivalent resultant force acting on this particle A, which is much simpler than those real 4 forces acting on the particle A. Okay, so how are you going to do it? If you want to use the trigonometry, that takes a lot of time. Okay, I'm not saying you cannot do it. You can still get it done, but it's much more challenging, which is really no need to do that. We are going to use the component method to solve the same problem. It's very standard, very straightforward. No matter how many forces, you just basically build a table, a chart, to solve this problem. And for those of you who are very familiar with a spreadsheet, like Excel or something, that's even simpler. Okay, so how are we going to do it? First of all, we need to establish x and y directions from this given one. So let's say this is the x direction, this is the y direction. So typically we always choose horizontal as x direction, vertical as y direction. Okay, so we get this. Then we just look at forces one by one. So instead of writing down those numbers, you can build a chart. So basically, we have a first column, which is called the force. You just put it down, F1, F2, F3, F4. These are the vectors. That's why you can put the arrow on top, indicating these are the real forces. And then you create a second column, which is called the magnitude of those forces. The magnitude of those forces are all given here. So F1, what is the magnitude? 150 Newton, right? What is the magnitude of F2? 80 Newton. What is the magnitude of F3? 110. What is the magnitude of F4? 100 Newton. When we talk about magnitude, because magnitude of the force is a physics concept, it's a physical concept. In other words, they are always positive. You can say, wow, this force going down, right? This force going down. Is this magnitude equal to negative 110? No. The magnitude is a physical quantity. It's always positive. But then you say, well, how about this force really going down? Because I can see it. And that's a direction. It has nothing to do with the magnitude. It's the direction. The direction is going down, or say it's going up. It has nothing to do with the magnitude. Magnitude is just how strong the force is when you apply. You apply this force, go to this direction, go to other direction. The magnitude is the same, but the directions can be different. Okay? So the second column we're going to create is to list all the magnitude from those four forces. In other words, from this picture, we just write down those magnitude here. The second column. And then we're going to create the third column and the fourth column, which are the x components and y component. Okay, so x component and y component. So going back to look at F1, which F1 we're talking about? This one, right? So F1, let's just do it one by one, right? So F1, the magnitude 150, the angle between this force and the horizontal x direction is 30 degrees. It's given from the original problem statement. So 30 degrees and 150. So in other words, this one is 150, and the angle between this one is 30 degrees. So if you already have this one with a 30 degree, what is the x components of this force 1? Well, that's f times cosine 30, right? So if this is a 30 degree, then f times cosine 30. What is f times cosine 30? 150 times cosine 30. And you punch your calculator, that should be 129. And then point something, right? 0.9. Okay, so that's x component. When we talk about magnitude, it's always positive. But when we talk about the components, sometimes it is positive, sometimes negative, depending on the direction. So we always assume x direction to the right is positive. That means to the left is negative. So when we have this x components of this force, obviously this component is to the right. If it's to the right, that's consistent to x direction, then you need to put a positive sign in front of that number. So f times cosine 30, you punch your calculator, you get 129.9. And then you need to put positive sign is because that's to the right direction. Any questions? After we get x components, then equivalently we can get y components of this force F1. So again, this is F1. What is y component? This is y components, or say this is y components. So that's going to be f times sine of this angle. So sine 30 is half, and then times 150, that's 75. And this is also consistent with the positive y direction. So that's why you put the positive sign here. That's a positive 75. Okay? So after we know the magnitude, we know the direction, we can calculate those two components, x and y. After we're done with this one, you move to the next, talking about F2. Okay? Going back to look at F2. This is F2. So F2 having the magnitude 80 Newton with the angle between this and y direction 20 degrees. Okay? So then let's go back to look at this one. So which is 80 magnitude, and the angle is what? Angle is 20, right? So then what is the x components? This is the x components, or this one. So then there's going to be f times sine of this angle, right? So f is 80 times sine 20, and you get 27.4 if you punch your calculator. Okay? However, the direction is to the opposite, to the left. the x component. And if that's the case, you need to put negative sign here. So finally, it's end up with x component F2 equal to negative 27.4. Okay, so don't forget this negative sign. When you punch the calculator, it does not give you the negative sign. This negative sign comes from the direction. You have to identify by yourself. Okay, y component. This is the y component of this force. That means F times cosine of this angle. So F times cosine 20, we finally end up with 75.2. 75.2 is the magnitude, is this one. This is also going up. That's why you have a positive sign here. Okay, so that is the x and y components for the second force. Number 3, we need to go back to look at force 3. This is the force 3. So force 3 having the magnitude 110 and then going down. In other words, this is the parallel to y direction, but it's an opposite direction. So then you even do not need to do the calculation, because from common sense, if you have a force going down like this way, then there's no x component, right? Because this is a perpendicular to x. There's no x component. No x component, put a 0 here. You have y component. Y component is this magnitude itself, 110, but it's going down. That's why you have a negative sign in front of 110. Okay, so that's called y component. So finally, we have one more force to go. That's F4. F4, the magnitude is 100 Newton. The angle between this force and x direction is 15 degrees, as given from problem statement. Then we can calculate the x component, y components. X components is going to be F times cosine of this angle, 15, right? Yes. So then this one, which is 100 Newton times cosine 15, and you get 96.6. So 96.6 is to the right. That's why you put a positive sign. And then y components, that's going to be F times sine of this angle, which is sine 15. F is 100 Newton times sine 15, you end up with 25.9. So the 25.9 is the y component, but the y component going down. That's why you put a negative sign here. Okay, so this is what I call using the spreadsheet. You build a table, you get all the components, then what? You just add them together, right? So add all these x components together, this one plus this, plus this, plus this, and this what is the result you can get. Similarly, you're going to add all y components together, and this is the y component of the resultant force. If it's a positive, then it's positive. If it's a negative, then it's negative. This time, these positive or negative are not determined by your common sense. It is determined by these values. You may say, why do I need to add those together? Because from fundamental principles we have here, we just need to add those together to get the x component of the resultant force, to get the y component of the resultant force, right? So after we got x components of resultant force and the y component of resultant force, actually you can stop there. If the problem doesn't specifically ask you what is the magnitude of the resultant force, what's the direction of the resultant force, actually you can just stop here. There's really nothing wrong. Because basically this is equivalent to plotting the x component, which is 199.1, and then plotting the y component with the 14.3, because positive, this is going up, because this is positive, that's to the right. So these are the two components of the resultant force. You can just stop there. But many problems would specifically ask you what is the magnitude of that equivalent resultant force. If that's the case, you go back to look at those two equations. This is the equation to determine the magnitude of that resultant force. That means you square the x components, add y, ry square, and don't forget to take square root. And that's called the magnitude. And the direction, using the angle to represent the direction. That means ry divided by rx, and then you take inverse of this tangent so that you can get this angle. Okay? And that's exactly what we do here. So we get x component, you square this one, you plus the y component square, and then take square root, and you get r. That is 199.6 Newton. And this is what I'm talking about. You square it, or you box it, or you can call it highlight. And that's a final solution. That's the magnitude of this resultant force. Further, you can calculate this alpha. This is the angle between the force and the x direction. And that is a 14.3 divided by 199.1. That's a tangent alpha, and then you punch your calculator again to get the inverse of this tangent function. You get alpha equal to 4.1, for example. Okay, so we solved the problem, right? Originally, we have 4 forces acting on this particle A. The equivalent, or called the virtual resultant force, is this, having the magnitude and also the direction. Okay? So these are the typical procedures for solving this kind of problem. So again, if you want to try using the trigonometry, I'm not saying you cannot get it done, but this is very straightforward. You see the procedures. If you have 100 forces acting on this particle, it's no different. You just create additional rows, right? And then you add them together. There's one thing I want to talk about, because if some of you are careful, you see there's some inconsistency between the way we're solving and the previous chapter comments I gave. The inconsistency comes from those numbers. So even the authors from the book sometimes may not follow what they talked about before. You know, the last slide in chapter 1, I talk about numerical accuracy. Okay, the final solution, if the first digit is anything other than 1, then you need to keep 3 digits. Okay? If the first digit comes with 1, your final solution should end up with 4 digits. Okay? So let's check here. So this is nothing wrong, right? Because it's 4 digits, because the first digit is 1. That's perfectly okay. This is okay because if you really want to write it 4.10, that's fine. Okay? Well, you ignore 0, that's fine. But in the middle process, actually there are some problems. Okay? These are what we call the middle process. These are not the final answers. So in principle, you need to have 129.9 and then something. I don't believe this next digit is 0. I don't believe so if you punch your calculator. This is 150 multiplied the angle of this 30, right? The cosine 30. If you punch your calculator cosine 30, it's not that simple number. So then multiply 150, it should have more. So in other words, in the middle process, if the first digit is 1, you need to keep 5 digits. Okay? This one, I hope that's the third digit is 0, but you may not. It is, because the sine 30 is exactly half. Okay, this is right. So that is correct. This is wrong, right? Because the first digit is 2. That means final solution should keep 3 digits. But this is the middle process. You should have a 4 digit. But anyway, I'm just trying to tell you, you try your best to follow that kind of suggestions. Okay, so in the middle process, you need to keep 4 digits if the first digit is not 1. You need to keep 5 digits if the first digit is 1. Your final solution, if the first digit is 1, then you need to totally keep 4. If not 1, then you keep 3. Okay. The bottom line for this one, back to this, you need to use the component method to solve the virtual, or called the equivalent, or called the resultant force, based on those existing real forces. So in other words, this one is equivalent to this. And our job is to calculate this blue force.